Developing Newton's laws, getting to Newton's great synthesis that brought together astronomy and physics to create astrophysics took 2,000 years. It started with the understanding that the Earth is round and ended with the understanding of gravity. Similar developments happen in optics, the study of light. Unfortunately, most astronomy textbooks, including ours, gloss over that fact. They usually start in the 19th century. The reason they do so is because that development happened to a great extent in places like the Muslim world, late Middle Ages, etc. Still, I believe the time has come to include some of these stories in our learning about science and astronomy. In this lecture, we will go along that route. We will introduce geometrical optics, a topic that originated in the ancient world and to which Newton contributed greatly as well. Interestingly, he also messed it up pretty much for a couple of hundred years in a way that reminds one of how Archimedes messed things up for the heliocentric system that Aristarchus thought up. Some thought was given to optics in ancient Egypt, but we do not know if they separated optics from spiritual learning. Probably it was the Greek Euclid that lived at around 300 BC, whose work you guys learned in Geometry 1 and 2 in middle school, that is credited with being the first to discuss the properties of light rays. Euclid's Elements is basically the book that's the most sold in the history of the world after the Bible. But that's not a book about optics, that's a book about geometry. Still, his impetus, his ideas about geometry were very much related to his thinking about optics. Optics is the study of light. He is the one that thought about how light moves usually along straight lines. Euclid's description of how magnification happens by light entering at larger angles rather than smaller angles will be something we will be using in looking at how telescopes work. Unfortunately, the Greeks thought of light in a little bit of a weird way as well. They thought, beginning with Socrates and Plato, that light comes from the eye, illuminated object, and moved at infinite speeds. Here's their logical proof. You wake up, you see stars. Those stars on the celestial sphere always look the same, unless you have clouds. But at night time, you never see a portion of the sky being suddenly disappearing. Okay? Now these stars are very far away. If the sun, for example, is on the other side of the Earth, and the Earth shades it, then suddenly we should see a portion of those stars disappear, because stars, according to them, are pieces of ice on the celestial sphere that reflect some sort of light. Where is that light coming from? Either it's coming from the sun or it's coming from our eyes. Well, if it's coming from the sun, you should see some eclipses. If it comes from our eyes and moves at infinite speeds, then you wouldn't see the eclipses. Hence, the light comes from our own eyes. Not bad, eh? Damn wrong, but not bad. Hero of Alexandria and Ptolemy, the guy that developed the geocentric model, developed optics further. Still, it was Persian and Iraqi Islamic scholars that gave huge boost to the field. That came in the golden age of the Muslim culture between the 9th and 13th century. First one was Ibn Sal in the 10th century, who developed optics to the point of actual usefulness. Only after him could lenses be fashioned into actual glasses that help people see, and into mirrors that can create reflectors, such as the projector you have in the front of your car and that lights the road. Alhazen combined these mathematical and experimental results with Euclid's work and other optics work from the ancient Greek and Roman world. Avicenna, or Ibn Sina, the inventor of Newton's first law, came in the 11th century and with brilliant insight saw that the speed of light cannot be infinite, and that light comes from, surprise, surprise, shining objects like the sun, which of course made those scholars think that stars shine of their own accord. Notice that this resulted in the understanding that not only that stars shine of their own accords, but that planets reflect sunlight, etc. This Islamic world did not develop as much after this golden age between the 1200s and the Renaissance 200 years later, possibly because of the Mongol horde invasion that killed 70% of all inhabitants of Persia and completely demolished the library, the biggest library in the world in Baghdad in 1258, at about the same exact time that libraries that were almost as large burnt in Spain and in present-day Turkey due to religious wars. In the early Middle Ages, Europeans learned ancient Greek astronomy and Arab science from Ibn Rushd of Spain, also known as Averroes, and Constantine the African, a Muslim Arab that converted to Christianity. The Europeans learned this Greek and Arab astronomy and science, and then started developing some ideas of their own. Robert Grotesete in the early 13th century and Roger Bacon late that century were both in England. They came with a new approach to science that combined those ideas with the principle of parsimony that we spoke of last week. That weird idea that the simplest explanation is best still holds. In Newton's century, two Dutch scholars, Snell and Huygens, developed an explanation of light that concluded that light was a wave. At the same century, Descartes in France independently invented a similar concept. Newton, however, preferred a view where matter is made of heavier atoms and lighter corpuscular particles. Only Newton said light moves faster in glass and water than it does in vacuum and in air. Wrong, wrong, wrong. Newton's idea caused most Europeans to avoid the correct interpretation of how light moves in matter for another 200 years. Let us turn our attention to a measurement that's independent of whether light is a wave or light is a particle. This is a measurement of the speed of light in empty space. Galileo was the first one to actually try and make that measurement. Galileo's idea was that he would go on one hill with a lantern and uncover it. He sent his assistant to another hill 10 miles away. That assistant would then uncover his lantern when he sees Galileo uncover his lantern. Going back and forth, they should be in principle able to measure how long it takes light to arrive from one to the other. Ends up light was way too fast for them. In modern terms, we may actually tell that this is less than a millisecond, and therefore humans cannot actually perform that without human response time being a factor that completely messes up the experiment. Ole Romer, a Danish astronomer in the tradition of Tycho Brahe, about 100 years after Tycho, is the one credited with figuring out the speed of light. Although his results were a little off, his method was solid. Here is how it works. Galileo Galilei, with his telescopes, discovered that Jupiter had 4 moons that he could see. Let's concentrate on one of that moons, Io, the closest to Jupiter. Io goes around Jupiter basically once every 2 days. Now, let's assume that you observe Jupiter from Earth, as in the picture below, in the beginning of the year, say in January. You're seeing Io hiding behind Jupiter at a certain time of the day. And then you go all the way to the middle of the year, say around June, and you're looking at Io again. Now, if Io is really going around Jupiter exactly every 2 days, you should see Io getting in behind Jupiter exactly at the same time. However, what Romer discovered is that you're seeing Io disappearing 16 minutes later. Now, if that is correct, that means that light from Io takes extra 16 minutes to arrive. That's because the distance from Jupiter to the other side of the orbit of the Earth is now 2 astronomical units further. Romer's mistake in the numbers was because at the time we still didn't have a very good number on Earth's astronomical unit, and because you had to involve a little bit of trigonometry, we also didn't have a very good distance to Jupiter. In 1729, James Bradley, a British astronomer, found a confirmation to the speed of light, an independent confirmation. The idea is a nifty one. By that time, people knew how fast Earth was moving around the Sun. Now, here is the mini experiment. Don't do that at home. Think about Earth as a car going, say, at 10 miles per hour, and say you're throwing a bottle of something into that car at 10 miles per hour. A passenger in the car, not knowing that they're moving, would see the bottle coming in at an angle of 45 degrees, which is the vector combination of those 2 velocities. Or, if you may, you can look at the right-hand side of this picture, and you will see that this is kind of similar to rain falling. If you're standing in the rain and rain's falling, rain falls directly at you. If you're running, then it looks as if the rain is coming at an angle that depends on how fast you run and how fast the rain's coming. That angle can then tell you the speed of the incoming rain. Same thing with light from a faraway star. If Earth is moving at an angle, at a 90 degrees angle to the star light, then we see that star, rather than being in the right exact direction of where we see it when we go towards it or away from it, we see it shifted by a little bit. Why? Because it looks as if the light is coming at that angle. Using this nifty idea, Bradley was able to figure out that the speed of light is fairly close to our current value of 300,000 kilometers per second, a very high speed, and yet not an infinite number. It took all the way until the 19th century to figure out the speed of light to a higher degree of accuracy. The trick was a trick by a French fellow by the name of Fizeau. Fizeau worked on Galileo's idea and did this thing. Light coming from a light source into a partially reflecting mirror goes through a cogwheel, through a toothed wheel, then bounces from a faraway mirror and back to the eye. Starts spinning that wheel. If you spin it at the right speed, then light goes through the tooth and exactly back through the tooth, and is not blocked by a tooth if you move at the wrong speed. So you spin up the cogwheel until you see the brightest dot. That means that you are going through the tooth. This nifty modification of Galileo's experiment yielded fairly accurate result, and similar experiments are still being used to the current value of 2.998 etc. times 10 to the 8 meters per second.